Here we go. So, hi everyone. Thank you for coming in. Thank you, Will, for coming and preparing this talk for us. To those who don't know him, Will is someone who's been working a lot on the analysis of the expressivity of different types of neural networks. I met him, I think, 3 years ago now in Florence when he had just done his undergrad thesis on understanding RNNs and their connection to automata. Since then, he's been a pre-doctoral researcher at AI2 and is now a doctoral researcher at NYU. And he's now working on transformers. So let's hear what you've been doing. Thank you.
Cool. Thanks, Gail. So today I'll be talking about our recent paper, Saturated Transformers, our constant depth threshold circuits. But I'm actually going to be giving a slightly updated version of this talk for some ongoing results. So basically, now we're removing this notion of saturation from the paper. So some of the assumptions underlying the proofs are changing, and we're also strengthening the results. So the new title is something like Transformers are uniform constant depth threshold circuits. And obviously I'll be explaining what these things mean as we get into it. But just to start, to give some motivation for this talk, I guess this was more for the first version of this talk I gave it more for a general NLP audience. So I don't know how compelling this motivation will be for you guys, but there's this narrative about scaling in NLP about whether if we make transformer language models bigger, this will enable them to have more complex reasoning, or whether there might be some kind of limits on just scaling up models and expecting better performance from them. So for example, models like GPT-2 have kind of really good story generation capabilities. And when you make them bigger, you get other capabilities like in-context learning or more local coherence, debatably. And this argument says that maybe if we just make these models bigger and bigger, we'll get even crazier capabilities in our language models. So that motivates this question of if we keep scaling up transformer language models, will their reasoning capabilities continue to improve? And this talk, I think it's obviously a theory talk. It doesn't directly touch on these type of questions, but I think it has some interesting implications potentially. So one interpretation of the results is scaling might not be all we need, which I think is not really that controversial of a take, but it's nice to have some theory that kind of relates to this position. So specifically, the connection that I see is that basically what we're proving in this talk is that transformers of any size can only solve computationally shallow problems. So problems that can be parallelized to a high degree. And in other words, problems that have a constant depth computation graph. And if you believe that shallow computation is not the same thing as efficient computation, in other words, the computation that can be done efficiently but not in parallel, then this implies that there are some kind of fundamental limits on what kind of reasoning you can expect in transformers. In other words, not all efficiently computable functions can be computed by a transformer. Another way to understand the motivation for this talk is just the conventional goal of opening the black box of neural networks. So specifically, we want to understand something about the computational model inside transformers. And if you have some kind of computation that a transformer is expressing, like what are the primitives that it's using? And when they're combined together, what kind of patterns or formal languages can those primitives let you express? Basically, by the end of the talk, one other way to understand these results is that they'll be showing that basically the transformer can be re-expressed in terms of one fundamental operation called majority. And through like the complex combination of different majority computations, you get a lot of different potential behavior in the model. So as some background, I'm first going to talk about the computational model of RNNs. This might be familiar to a lot of people here, but with RNNs, there's been a line of work trying to relate the expressive power of RNNs under various settings and various assumptions to the Chomsky hierarchy. And obviously the Chomsky hierarchy is nice because it has these connections to our theories of natural language grammar. And also we just have a lot of nice theory to understand and have good intuitions about what these classes mean and how powerful they are. So starting with element RNNs, or the most basic kind of RNNs, They look kind of like this. You have an input sequence and you have this autoregressive layer of hidden states that feed into one another. And this kind of looks like a finite state machine, right? And it turns out that if you assume saturation, which is the simplifying assumption for the RNN network, under this assumption, basically the hidden state vectors end up being equivalent to finite states in a finite state machine. And this means that the expressive power of saturated RNNs is basically the regular languages, or in other words, these models are equivalent to finite automata. So that gives kind of a nice way to understand what the model computation inside this architecture is. And here's just placing the RNNs in the Chomsky hierarchy. Of course, there's other types of RNNs besides the element RNNs. Specifically, LSTMs are this other variant of RNNs that have a more complex gating function. And it turns out that the gating function of these LSTMs is actually not just more complicated, but more expressive. So it can basically maintain more than a finite number of states as you process a sequence of length n. The number of states grows with n. And this enables kind of counting behavior. So if you have a sequence like a to the n, b to the n, your state vector doesn't necessarily act as a finite state, but it can act as like an integer that's tracking the value n and grows. This sentence gets longer. And this allows you to accept languages outside the regular languages. So this graph is from a experiment from Weiss et al. 2018, where basically you can see the value of the hidden state vector in this trained LSTM is tracking n in the input sequence. And yeah, so this gives us a nice way to understand the difference between LSTMs and RNNs, and understand basically that this capability of counting is kind of separating their abilities and giving them a different model of computation that lets them solve different problems and potentially with different inductive biases. So the natural next question is, what about transformers? Because transformers are really what people use in practice these days in NLP to process language rather than RNNs. So we'd like to be able to relate these to the Chomsky hierarchy as well. Of course, immediately we run into a problem conceptually if we try to do this, because there's no autoregressive structure in the transformer computation graph. So unlike the RNNs, where you have this left to right processing, it kind of looks like an automaton of some kind. In the transformer, you really just have parallel computation over a sequence. So you have this encoder block that's processing every input in parallel, and then you get kind of a vector of outputs, and then you kind of apply these parallel computations forward on some other dimension. And this means it's probably going to be hard to get any kind of theoretical result that relates these two automata, because there might not be a strict they might not be comparable, basically. Of course, what we could do is pick a different model of computation besides automata to try to understand what's going on in transformers. And that's basically the direction we're going to pursue here. So like I said, transformers are basically doing parallel computation over sequences. And one way to formalize this in theoretical computer science is with circuits. And that's what we're going to be doing. We're going to be showing correspondences between transformers and different classes of circuits in this paper, because that turns out to be basically a better goal than comparing them to automata. So that is going to bring us on a detour into circuit complexity theory. For those of you who were at the talk last week, you probably got some of this background already, but I'm going to go through it very briefly. So circuit complexity is basically the theory of computational hardness with parallelism. So conventional complexity theory asks questions like, how many resources do you need to solve some problem when you're implementing a solution on a serial Turing machine? Circuit complexity theory asks similar questions, but the programs you're writing are specified by circuits, which are kind of inherently parallel devices. So what is a circuit then? A circuit is just a directed acyclic computation graph. So it's made up of input nodes that represent bits typically. So this is x1, x2, x3 in the example. And then there's some internal nodes which represent basic logical functions like and, or not, and an output node, which is basically the output of the computation. In this case, the output node is the top node, the or node. And then if we want to evaluate the circuit, what we do is we take the input string that we want to feed in, which is a binary string. We assign those values to the leaf nodes in the circuit, and then we propagate forward through the circuit until we reach the output node. And at that point, we take the value that we've computed in the output and call that the output of the circuit. There's a couple natural complexity measures that we're going to introduce. Remember that circuit complexity theory is measuring circuits of kind of bounded resources. So we need to define what these resources are. The first one is circuit size. This is basically just the number of nodes in the circuit. So here size is something like 6. And you can think about this as the runtime without parallelism, because if you're going to run this circuit and you had no ability to parallelize at all, you'd have to just have a for loop over all of these nodes, basically, or just traverse these nodes somehow and execute each one. But there's this other complexity measure called circuit depth, which represents basically, or is defined as the longest path from the input to the output. So in this example, it's 2, because you can get from the OR node to any of the input nodes with just 2 jumps. And in contrast to size, depth corresponds to the runtime with parallelism, because basically, if you were going to execute this circuit with optimal parallelism, you could take all of the nodes at depth 0, execute them in parallel, and then you have all of the inputs to the depth 1 nodes, you could execute those, and so on and so on. So depth is really what we're going to think about as runtime in the parallel setting. So that's circuits. Now we're going to talk about transformers as circuits. So basically, one thing you might want to do is simulate a transformer with a circuit. And if you can do this, this establishes, or with a family of circuits. And if you can do this, what this establishes is that the problems that the transformer can solve can also be solved by circuits of a certain size and depth. And if we understand kind of what problems can be solved with a certain size and depth, that tells us what kind of problems the transformer can also solve. So last week, there was this talk by Howe et al. About hard attention transformers. And basically their main result is showing that hard attention transformers can be simulated by polynomial size constant depth circuits. And to unpack this a little bit, polynomial size means that basically the size of the circuit, so the number of nodes, grows polynomially in the input sequence length. So if you have a family of circuits processing inputs of different sizes, as the input size gets really long, the size of the circuit just remains polynomial in that input size. Constant depth means that basically the depth of the circuit is independent of the input sequence length. So no matter how long your sequence gets, you maybe only have like 3 or 5 or some other constant number of layers in your circuit to compute with. And finally, hard attention is just this simplifying assumption about the transformer that says that in the attention weight functions, basically they form one-hot distributions over the input. So they're selecting individual positions rather than splitting probability mass over different positions. So what are the implications of this result? Well, if you believe that hard attention transformers are a good model of practical transformers, this actually is a really strong result about how weak transformers are, because constant depth circuits can't solve very basic problems like parity, majority, or certain regular languages that are kind of similar to parity in different ways. And this is a classical result in circuit complexity theory. But the hard attention assumption is kind of strong, especially because in practice, people have shown that transformers rely on basically counting in similar ways to LSTMs. So in the same way that LSTMs can kind of use their memory to compute sums, like in the A to the n, B to the n example I showed previously, transformers can also split attention and take a kind of uniform sum over different positions to get that kind of behavior. And this is not possible with hard attention, but it is possible with soft attention. And it seems like maybe this mechanism might be giving the model more expressive power. So that motivates us to ask in this paper, what about with soft attention? Can we derive some kind of similar circuit bound in this setting? And the first thing we see if we think about this is that soft transformers are not going to be simulatable by constant depth circuits. So why is this? Well, I mentioned on the last slide that there's this language called majority, basically, which is asking of a bit string, are there more ones or more zeros in that bit string? So for example, 11100 would be good because there's 3 ones and 2 zeros, but 11000 would be invalid in this language. And this, like I mentioned, is known to be beyond constant depth polynomial size circuits. But it turns out that a 1-layer soft attention transformer can recognize majority. And the intuition for why is pretty straightforward. So it basically goes back to this counting ability that I mentioned on the last slide. You can basically take a uniform attention head that just averages everything to compute the average token. So in other words, for 11100, this head would compute 3/5. And then you can just threshold that average token value and check whether it's greater than 1/2 of the sequence length or not. And this gives you a really simple way to recognize majority, and just using what we know about majority and circuit lower bounds, we see that soft transformers are more powerful than constant depth circuits, or at least there exists some language that soft transformers can recognize that constant depth circuit families cannot. So the natural next question is, does this mean that there are any bounds on what soft attention transformers can do, or do they end up being Turing-complete? And there is this prior work that shows Turing completeness of soft attention transformers, but it relies on some pretty strong assumptions, in my opinion. So specifically, it assumes infinite precision of the transformer hidden states. And it also assumes basically that the feed-forward networks in the transformer have arbitrary computational power. So if you have this kind of transformer, the assumptions are quite strong. And I guess I'm just going to go through the proof a little bit to kind of show why I think so. So the way this proof works is you have an input sequence. Let's say it has 512 tokens in it, which is kind of typical for transformers. And the first layer basically uses self-attention to just pool all of those inputs into one position. So you now have at each position in the transformer a fixed length vector that represents a sequence of 512 tokens. And this very clearly relies on having infinite precision, because if you have any kind of practical limits on precision, you're going to have a lossy encoding of the sequence, and you're not going to be able to store all of it in this vector. But once you do this, the second layer, or the next sublayer of the transformer, basically uses the universal approximation of the feed-forward network to just compute any function you want as an oracle. So if you want to solve a language with indicator function f, you just construct the feed-forward network to compute that indicator function over this input that's been encoded into a single position. So I think this proof feels kind of like it might not describe practical neural nets, because it relies on this lossless encoding, and then it also relies on learning this really potentially complex function in the feed-forward neural net. So basically what that motivates us to do is to introduce some kind of constraint on the precision or the complexity of the feed-forward nets, and see whether the power of the transformer gets reduced. So in the original paper that is on arXiv, the constraint that we introduce is saturation. In the version I'm going to present here, we are using a different, potentially more general constraint called log precision. So what does log precision mean? Basically, log precision says that the transformer values have order log n bits of precision on sequences of length n. So log n bits of precision is basically enough to represent positional encodings or pointers, which is why we give the transformer this much precision, because it's important in the transformer that you have enough precision to encode position in the input layer, or else your model just reduces to bag of words, basically. And also, it allows you to maintain pointers to other positions in the transformer throughout the processing of the sequence. And this is probably important if you want to implement some kind of distributed computation over a sequence. Importantly, though, it's not enough precision to fully pool the input sequence into one value, like we saw in the last construction. So you can't just pool n different bits into one position and use the feed-forward network to compute some black box function over that full sequence. And this is going to give us, basically force the model to be truly distributed in some way, rather than just kind of reducing to using its feed-forward network in a non-distributed way. This is also kind of a standard assumption for analyzing streaming algorithms or sorting, like that you have a sequence of n items with log n precision. So it's kind of nice in that sense, just because it resembles a way that people analyze other problems. So given this assumption, what are we able to show? So basically what we prove is that log precision transformers can be simulated by polynomial size, constant depth threshold circuits. And here a threshold circuit is a generalization of the circuits I talked about previously, and I'll define exactly what it means in a second. So threshold circuits look a lot like normal circuits, except they have this additional gate called majority. So specifically what majority does is basically compute a majority vote of all of its input. So it's kind of like an oracle to this majority language that I described a second ago. So maybe it takes in 3 bits, 1, 1, 0. It takes a vote of those bits and it will return a 1 in that case. And because you could express any standard circuit as a special case of a standard circuit, of a threshold circuit, and also because majority we know is beyond the capabilities of standard circuits, we see that threshold circuits are going to be basically strictly more powerful than standard circuits. So how does this proof work to show that transformers with log precision can be simulated by threshold circuits? Well, here's a picture of a transformer layer at a high level of abstraction. Basically, we're going to be constructing a circuit that simulates this layer on length n inputs. So what we can do is basically first look at the unary or binary operations in this circuit. So these are the operations that take basically a bounded number of inputs. So the feed-forward network is one of these examples. Also these S functions that basically compute the score between 2 different tokens. And we can apply basically the techniques from Howe et al. To replace this part of the network with a standard circuit. So this is a circuit of constant depth and polynomial size without any threshold gates in it. But now we need to somehow remove this average component of the circuit and of the transformer and simulate that with a circuit. So it turns out that that can be done with a threshold circuit. This is kind of a classical result about threshold circuits, that if you have n numbers with log n precision, you can compute their sum, and an average is basically just a sum of n numbers. So that's how we do that. And because standard circuits are a special case of threshold circuits, this whole thing can actually be considered to be one large threshold circuit. And because there's only a constant number of layers, if we stack a constant number of these circuits on top of each other, we end up with basically just one constant depth polynomial size threshold circuit. So the other piece of this is basically showing that these circuits are uniform. And uniformity is the condition that basically says that circuits for different lengths are not too different from each other. So in other words, if you're processing n tokens versus n+1 tokens, the circuit you get for those different lengths is going to be not that different. And formally, what we show is that this construction is log space uniform. So that means that there's a Turing machine that uses log space that is able to construct the circuit for size n as a function of the input n. The details of this are not that important, but it basically involves just constructing an algorithm for a Turing machine that will print this circuit in some serialization, rather than just showing that the circuit family exists. So what are the implications of this result? So the first, I guess one of the things I mentioned was trying to understand the computational model of transformers. So one way to interpret this result is that if we have a transformer, we can rewrite its computation graph in principle just as a polynomial number of majority gates stitched together in a way that has only constant depth. And in this sense, maybe majority gates are all you need. That would be one way to describe transformers, or at least this is one valid way to write transformers as functions. And because we kind of know what can be done with majority gates, like majority gates can be combined to do things like compute averages or sums, or sorting. This suggests that maybe these are the kind of things that are implicitly happening inside a transformer, although this is kind of speculative. The other kind of implications we can draw from this is for analyzing limits on transformers and the types of functions that transformers can compute. And this is going to relate to kind of some conjectures in complexity theory. Basically what we've proven in this with this result is that log precision transformers can only solve problems in the complexity class called TC0. And TC0 is basically just directly defined as the problems that constant depth threshold circuits can solve. And in this Venn diagram on the right, TC0 is the second class up from the bottom. AC0, the bottom class, corresponds to hard attention transformers. So AC0 is constant depth normal circuits, TC0 is constant depth threshold circuits. And TC0 isn't really, we know that it's more powerful than AC0, but we don't really know where it falls in relation to other classes. So for example, it could be that it's equal to P, kind of in like the most extreme case, or it could be separated from a couple other classes between P and TC0, like L, log space, or NC1, another class of circuits. And it turns out that what we believe about these separations has implications for how powerful transformers are. So if TC0 is a proper subset of NC1, then it turns out that transformers can't recognize all regular languages. Just because if TC0 is a proper subset of NC1, then it follows that there's a regular language that is not in TC0. And similarly, so that's probably like the strongest conjecture you could have about how weak TC0 is. A much weaker conjecture is just that TC0 is a proper subset of P. So in other words, this class of very constrained parallel circuits is not equivalent to general polynomial time computation. No one has proved this, but as far as I understand, it seems likely. If you accept this, then it follows that transformers can't compute all polynomial time functions, just basically by definition of those classes. And yeah, this suggests that there's basically some kind of efficiently computable function that can't be expressed inside a transformer.
You're getting a comment in the chat.
Yeah.
That you should probably point out that here you're discussing transformers that are uniform or the other constraints, log space uniform, because indeed, if you weren't assuming that these were uniform or polynomially generated circuit families, then AC0 is not contained in P. It could even recognize things that aren't computable.
Right. So that's a good point. The notation for these classes is kind of overloaded. So I'm in this Venn diagram, I mean the uniform variants of these classes, but oftentimes the non-uniform and uniform versions of AC0 or TC0 are written the same way, and it just, one paper will define them one way, one paper will define them another way. But in this diagram, I'm talking about the uniform classes. Yeah. Specifically
generated in log space or polynomial time, or okay.
Log space uniform. Yeah.
Okay, thanks.
Yeah, so this is kind of the speculative implications for limits on transformers coming from this result. There's kind of a more general, even more speculative version of this argument that I wanted to just briefly point out, which we're calling like a parallelism tradeoff. So this is basically an idea for why there are kind of limits on any large scale language model, not just any transformer model that might emerge from basically large scale pre-training. So the argument goes something like this. So as a basic premise, we're going to say that scaling any model to be large requires parallelism, basically because if you want to train a model on a lot of data, you need to be able to parallelize that training very efficiently. And for the purposes of computational complexity, let's say that parallelism means that the expressive power of the model is a subset of L. And then there's a conjecture, obviously, that not all efficient computation is parallelizable. So in other words, L is a proper subset of P. And therefore, we can conclude that any scaled up model must sacrifice some kind of expressiveness. So there's some kind of efficient function, efficiently computable function that it cannot express as a result of the fact that it has to be parallelizable to be trained at massive scale. So I think this kind of relates to this question about scaling up and large scale models in NLP. So if we think that maybe, I mean, this doesn't say that there are like useful problems in P that models won't be able to do, but it does say that there might be some kind of limits, and maybe it at least raises a question about whether scaling up is the right way to build models with complex reasoning capabilities. So that's the end of the main results. I also wanted to just mention one other brief thing that we included at the end of the paper. So this is a positive result or a lower bound for what transformers can do in the context of instruction following. So basically what we are showing is that transformers can execute instructions encoded as threshold circuits. So what I mean by this is you have an input, let's say a string encoding 5, 10, 4, and then you have an advice circuit. So basically this is a circuit that gets concatenated to the input and provides some kind of instructions for what to do with that input. So it's like a program that you want to execute over the input. You can understand it to mean something like add the numbers and return true if the sum is even. What we're proving is basically that there's a transformer you can construct that can do this if the advice is a constant depth threshold circuit. So basically, we showed constant depth threshold circuits are kind of like an upper bound on log precision transformers. And we also show that if you give them this kind of additional advice, it's also kind of a lower bound on what they can do. Although it's not really a lower bound in a precise sense. So we're not really showing, yeah, it's kind of the closest thing we could get to a lower bound. And hopefully in future work, us or somebody else can refine this. Yeah. So just to summarize a little bit, basically the main result of our paper is just that log precision transformers are constant depth threshold circuits. And one way to understand what this means is that you could take a transformer and you could rewrite its computation graph in terms of majority gates, and you would have only a polynomial number of them and a constant depth. And majority gates can do things like summing and sorting, etc. So maybe these are the kinds of things transformers can do as well. And another way to interpret this is kind of thinking about what transformers can't do. And the limits that emerge are basically the transformers can only solve shallow problems, where shallow means problems with a constant depth computation graph under this particular type of circuit. And this implies some kind of limits on transformers if we accept certain conjectures in complexity theory. And then finally, we also showed this thing about instruction following and are hoping that maybe we can also try to characterize lower bounds on what transformers can do to get a more precise characterization of the power of transformers. So thanks.
Thank you. So you made a constructive proof for how transformers can follow, the sort of like transformers are universal circuits. I don't know what to call this. You really implemented receiving a circuit as an input?
Yeah, exactly. So I will say that, so yeah, this is something that it's not in this is something that's kind of work in progress. But I guess we haven't like written the weights down. So we're still kind of assuming that you can kind of like with RASP that you can compute any kind of basic functions you want in the feed-forward network, and we're not worried about like the neural implementation of those functions. So there are some caveats there, but it is like a constructive example of a transformer that can do these things.
Cool. So at this point, I'm going to turn the recording off because people want to have a more informal chat. So goodbye to everyone who's watching from home.